Hello everyone, thank you for joining today. I'm Les Quindipan and I'm a sales application engineer with Listen Inc. Today I'm joined with Christopher Hett of Portland Tool & Die. I'd like to welcome you to today's seminar on Bluetooth audio testing. We would also like to extend a thank you to S&V Sanford for their help in organizing this presentation. Listen and Portland Tool & Die share a common goal of developing modular and flexible audio test tools. To start, I'll hand things over to Christopher, who will explain the Bluetooth interfaces in detail. Afterwards, I will show how the interfaces seamlessly integrate with SoundCheck, and we'll perform some measurements with the Bluetooth headset as well as a Bluetooth speaker. Okay, on to you, Christopher.
Thank you, Les. My name is Christopher Hett, and I'm the president of Portland Tool & Die. Today I'd like to introduce you to our company and our products. Portland Tool & Die was established in 2011 in Portland, Oregon, with the aim of building modular audio test and measurement tools. Like Listen, we believe in modularity and flexibility when it comes to building test systems, and we have focused on building cost-competitive interfaces that extend the functionality of traditional audio test systems like SoundCheck. The advantage of this strategy is that your test system can adapt as your product portfolio changes. For example, if you're currently making analog headphones and now want to release a Bluetooth headphone, there's no need to buy and learn a whole new test system. You can just add the new interface to what you already have. Also, with new audio formats appearing all the time, modularity means that your test system is never going to be obsoleted. You can simply add new capability. We've worked very closely with Listen on the control side to ensure that control for all of our interfaces is available directly within SoundCheck. So if you're already a SoundCheck user, there will be minimal learning curve when adding our products. Our current product lineup includes MEM microphone interfaces, I2S interface, and Bluetooth audio interfaces. So let's focus on our Bluetooth interfaces. We offer two Bluetooth interfaces, the BTC4149 shown on the left and the BQC4149 shown on the right. The BTC is a larger instrument intended for R&D use. It has a touchscreen for easy local control and can be controlled by the SoundCheck software over USB. The audio is available over USB as well as SpeedF. The BQC is a smaller, more ruggedized version that's intended for manufacturing applications. It does not support SpeedF, USB audio only, and it is powered and controlled through the USB interface. In the following video, I'll show you these two products side by side. As you can see, the BQC is small and has a ruggedized metal enclosure. For simplicity, it has just one USB input for power and control, and the Bluetooth antenna. The Bluetooth antenna is connected to the instrument via an SMA connector. This allows the antenna to be removed and placed inside a test chamber, and the test PC and Bluetooth audio interface can remain outside the test chamber. The BTC is a larger instrument designed for benchtop R&D type use. It can be controlled directly from the front panel touchscreen or remotely through the USB interface. Using the front panel, you can discover and connect to other Bluetooth devices. If you know the Bluetooth address of the remote device, you can enter its address directly without having to spend the time doing an inquiry. You can also control the audio streams as well as the audio source directly from the front panel. This device has a larger right-angle antenna, which can also be removed. The connector on this device is a standard N-type coax connector. The back of the BTC offers additional connection options. Here we have the power input and the USB interface. The BTC requires 12-volt DC power, which is provided by a universal AC to DC power adapter. It cannot be powered from the USB connector. In addition to the USB audio, this device also offers SpeedF input and output for easy connectivity to existing test systems. Now let's switch back to the slides to take a deeper dive into the details of these devices. In general, the idea behind all of the Portland Tool & Die audio interfaces is to convert between audio formats that are difficult to access into standard audio interfaces. We have focused on using native USB audio and SpeedIF because these two standards are widely available. SpeedIF is commonly found on many types of older as well as newer analyzers, which means that you can connect an existing analyzer to the BTC 4149, control it from the front panel, and get audio in and out over Bluetooth. USB is on all modern PCs, and the desktop operating systems natively support USB audio. So these audio interfaces will work with Windows, Mac OS, and Linux. USB control is particularly convenient when using SoundCheck, as it enables the device to be fully controlled within the software and used directly in test sequences. Les is going to demonstrate that a bit later on in this presentation. Now let's talk about how the PT&D solutions compare to some of the other common Bluetooth interface options. Eval boards and dongles might be less expensive, but they don't offer the same functionality, and there are definitely some significant trade-offs. First, let's talk about the durability and longevity of the product. As you have seen, our products have durable metal enclosures with heavy-duty connectors. These connectors are decoupled from the internal circuit boards, so the force of connecting and disconnecting is handled by the enclosure, not the PCB. You might find that some eval boards have RF connectors, but those connectors are typically soldered directly onto the circuit board, and it's relatively easy to damage that kind of connection by over-tightening or pulling on the cable. A dongle is more robust, but they're small and easy to lose, and it can't be located very far away from the PC system. For availability, I'm referring to the ability to purchase the product over time. If you're manufacturing something and you need to add capacity, you need to be able to purchase the same test equipment year after year, possibly several years into the future. Our interfaces have a long product life. We've been building them for many years already, and even if the internal Bluetooth hardware needs to be changed, the interface exposed to the test system will remain unchanged, so it will introduce no disturbance to the manufacturing line. For an eval board, typically the availability lasts just a little bit longer than the IC introduction cycle. The Bluetooth technologies are evolving quickly, and there are lots of manufacturers that are pushing new chipsets. So every time they release a new family of ICs, a new set of eval boards comes out, and you can no longer buy the previous version. So if you've developed a solution on one specific eval board, and then it goes EOL, you'll need to invest more time in changing your solution to the new eval board. The same thing often happens with dongles. Typically, the availability is a little longer than the eval boards, but the life cycle of the dongles basically follows the same Bluetooth introduction cycle. Maybe it's just delayed by a year or two. The other thing that has a major impact on test systems is having a consistent software control interface. With the PT&D solution, all of the devices can be controlled over USB, and they support the same command set, and that command set will be supported in the future. With dongles, basically there is no control interface other than what the OS gives you. Typically, the OS does not allow you to control the low-level Bluetooth details, and there is little to no feedback related to the status of the Bluetooth interface. As mentioned earlier, the antenna can be cabled to both the BTC and BQC. This allows the host PC and the Bluetooth audio interface to be located remotely away from the antenna in the test chamber. When using an eval board, if it does not have a detachable antenna, the eval board will need to be placed inside the test chamber. If you're using a dongle, the test computer will need to be located physically close to the test chamber, and a USB cable will need to be routed into the test chamber to connect to the dongle. The next area where the PT&D solution gives you much more control is the ability to control the Bluetooth links at a low level. You can select which codec you want the device to use for both the A2DP and HFP link. You can open and close the A2DP links independently. With the BTC, you can view the selected codec and link status on the Bluetooth audio stream directly from the front panel. For both the BTC and BQC, you can use the USB interface to query the current Bluetooth status from the host test system. Eval boards typically use LEDs to indicate this kind of status information, and even if there is an interface for the test system to interact with, there's no standard control interfaces from board to board. With the Bluetooth dongle, you're limited to what the operating system exposes, and typically the OS will typically only indicate the Bluetooth connection status. But you really don't have visibility into which profiles have been opened and the status of the audio stream or which codecs are in use. The last two topics I'd like to discuss are EMI and ESD protection. As you've seen, both the BTC and BQC are housed in tightly sealed metal enclosures. These enclosures provide a high level of EMI and ESD protection. Eval boards typically don't come with any kind of enclosure, so they can be a source of unintentional electromagnetic radiation, as well as being susceptible to external electromagnetic energy. Since all of the components on the eval board are exposed, they can also easily be damaged by electrostatic discharge. Dongles typically have better EMI performance than eval boards, but they are often housed in plastic shells, so they can be damaged by ESD when they are disconnected from the PC host. Now let's talk about the differences between the two PT&D Bluetooth products. Both products use the same standard USB audio interface, and they both support 48 and 44.1 kHz sample rates. In addition to the USB audio interface, the BTC also supports the SpeedIF interface that can run at either 48 or 44.1 kHz. The Bluetooth standard states that a Bluetooth audio device must be either a source or sync type device. The source type device sends audio to a sync type device. In order for two Bluetooth audio devices to connect, they need to have opposite roles. A source is not allowed to connect to another source, and a sync is not allowed to connect to a sync. An example of a source might be a cell phone or Bluetooth microphone, and a sync type device might be something like a smart speaker or a headphone. The BTC can be configured to act as either the source or the sync, but the BQC has a fixed role as the source type device. The A2DP and HFP profiles both use a selectable codec to encode and decode audio transmitted over the Bluetooth link. The Bluetooth standard mandates that both the A2DP and HFP profiles support at least one common codec, but it also allows the devices to support an extended set of codecs. For the A2DP profile, the mandatory codec is SBC, and for HFP, it's the CVSD codec. In addition to the mandatory codecs, the BTC supports several additional aptX codecs. If the remote device also supports the aptX codecs, the two devices can use the aptX codecs to transmit higher quality audio. Both the BTC and BQC support the mandatory CVSD as well as the MSBC codec, which is used to transmit wideband speech over the HFP link. For controllability, as we discussed earlier, both devices support remote control using the USB interface, and the BTC can also be controlled directly through the local touchscreen. One important note about the USB control interface is that the set of supported commands is the same for both BTC and BQC. This means that if you write a test in the lab using a BTC, porting that test to run on the BQC is simple. And in fact, inside of SoundCheck, it's almost seamless. And finally, just another comment about the antenna connectors. The BTC has a standard N-type connector, and the BQC uses a standard SMA type connector. One of the benefits of using these standard connectors is that you can easily order pre-built cable assemblies, and it's easy to find adapters to go between various other RF standard connectors. Alright, let's talk about how the Bluetooth interfaces can be integrated into your test system. Both the BTC and BQC can be controlled through the USB connection. PT&D provides a simple Unix-like command line interface for each instrument. This command line utility can be used interactively from a command prompt or integrated into other programs, scripts, or test executives. Listen has taken this integration to the next level by embedding the low-level instrument commands directly into SoundCheck. This means that all the commands can be accessed using a familiar interface, and most importantly, can easily be integrated into your test sequences. All of the commands are performed directly from the sequence message steps. Another nice thing about the integration with SoundCheck is that it will automatically recognize any PT&D Bluetooth device that's connected to the SoundCheck computer and will prompt the user to connect to that device. On confirmation, the device data is automatically imported into the hardware table and is ready for use. So, in conclusion, these devices can work as a standalone audio interface, but the way Listen has integrated them into their SoundCheck software really makes them a seamless extension of the SoundCheck system. Simple setup, easy to configure, and of course, you can reap all the benefits of being able to integrate them into your test sequences. That concludes the Portland Tool and Die portion of this seminar. Hopefully, I've given you a good overview of the PT&D Bluetooth audio interfaces and the pros and cons of these over other options. I'm now going to hand the presentation back to Les, who will show you the integration of these devices into SoundCheck, and will demonstrate them being used in a couple example test sequences. Thanks for your time and attention. Back to you, Les.
Thank you, Christopher, and thanks for that excellent in-depth look at the Portland Tool and Die Bluetooth interfaces. In this section of the presentation, I'd like to show you how the Bluetooth interfaces seamlessly integrate with SoundCheck. As Christopher indicated, the Bluetooth interfaces can operate standalone, but when combined with SoundCheck, not only can we have integrated software control, but we can really take advantage of capabilities unique to SoundCheck that combine for a powerful and easy-to-use Bluetooth audio test system. So let's start with the diagram of a Bluetooth headset test setup. In this setup, I'm using a BTC that has a single connection into the PC, and I'll pair the Bluetooth device under test. In our example, we'll test a headset as well as a speaker. Audio drivers for the BTC and BQC install with SoundCheck. The hardware is true plug and play, and this means I can plug USB directly into my computer, power on the interface, and the inputs and outputs auto-populate. You'll see I have 2 digital inputs and 2 digital outputs for the BTC. And SoundCheck is really adaptable for supporting mixed signal. This means I could have analog and digital hardware in one session. And the sampling rate supported for the BTC is both 44.1 and 48. I've set this to match the sampling rate of my Amp Connect 621, and I'll explain why we do that a little further down. In the Listen Hardware tab, you'll see that the BTC is also auto-populated. Here's where I may want to assign a startup default if I so desire. So Bluetooth signal paths are created in the calibration window, and I'll open this very quickly. On input, I have created a Bluetooth headset microphone signal path. You'll see the physical input on the BTC 4149 on the right, and the calibration file. On output, I have 2 configured Bluetooth output signal paths, BT out 1 and 2. The output could be used for sending a test stimulus to a Bluetooth speaker, or sending a test stimulus to the left and right ear of a Bluetooth headphone or headset. It can even be used to send wireless stimulus to a Bluetooth automotive head unit. That would be very useful for testing audio inside of a vehicle. Both the BTC and BQC have 2 ways of doing software control. Bear in mind I've got a BTC connected, but what I'm demonstrating works equally well with the BQC. The software installs a command line utility into the program files folder, and I've created a shortcut to that command line utility. It's down in my taskbar. Okay, and I'm just going to type a very simple BTC command. Let's just do help. And this will actually populate the list of software commands that can be used to control the BTC. So Kris had emphasized that these can run standalone. In a standalone test operation, you might use the command line utility for software control of the BTC. SoundCheck has integrated software control of the BTC, and this is done via message steps. If I expand the list of message steps in my step template library, you'll see some built-in BTC message steps in SoundCheck. This means it's very easy to develop a Bluetooth test sequence by clicking and dragging the step from the step template library into my working sequence on the right. And that's what I have here. You'll see message number 4, 5, 6. These are BTC message steps. Let's look at a few. So let's double click on the BTC get address step. And this step will query for Bluetooth devices in range and pair them to the BTC. Here I could set the inquiry time. In some cases, I can bypass this step and force the MAC address into SoundCheck. And that's really useful if you want to speed up test time, for example, a production line. Following the get address step is a BTC connect audio step. We'll look at that as well. Okay, here is where I will designate the profile and codec of the Bluetooth device. So here I am using an A2DP connection. If I wanted to define the codec selection, I just drop this list, and for example, if I had an aptX or an aptX HD device, I may want to designate the codec. We'll come back to the sequence, but I want to take a brief detour and talk about resampling and frequency shifting in SoundCheck. The trade-off of a modular system is that while it can be cost-effective to add a Bluetooth interface to an existing SoundCheck system, we may encounter sampling rate and sampling frequency errors that are a result of having two different interfaces connected to a SoundCheck system. SoundCheck analysis requires that the stimulus and response waveforms have exactly the same sampling rate. Any differences, for example, 44.1 versus 48, would result in an error. Fortunately, my 621 and my BTC have the same sampling rate as we saw in my hardware setup earlier, so a resample post-processing step will not be required. Once we resolve sampling rate error, we may have to make slight adjustments to correct for sampling frequency errors. This is a result of two hardware interfaces connected to SoundCheck that have very slightly different internal clock crystals. We could do that with a frequency shift post-processing step in SoundCheck. So how does frequency shift work in SoundCheck? SoundCheck can identify the centroid or center of gravity in a fixed tone and align the stimulus and response. This is great, however, it only works with sine waves. So SoundCheck has a great solution for this, which is called a compound stimulus. And what we can do is we can prepend a 1K tone at the beginning of my test stimulus, and that would be used to align the frequency shift step. So let's look at that in SoundCheck. I'm going to open up this first stimulus step. And this is, again, what we call a compound stimulus. You'll see I have two parts of my test stimulus. And this first part is that 1K tone, and below it is the actual test sweep. You'll see that that goes from 20 kilohertz to 20 hertz at a 12th octave resolution. But if I open, this is the prepended pilot tone, you'll see it's very short, 250 milliseconds. And most importantly, I have this set not to analyze. So the sole purpose of this prepended tone is to align the frequency shift. Okay, so once I frequency shift the recorded waveform, now I could do an analysis where I compare the original stimulus against the frequency shifted version of the recorded response. Okay, let's pull this all together. I'm going to run the sequence, but I want to highlight a few things in the sequence. This is effectively a headphone test sequence where I send a stimulus, get an acquisition, and do some analysis. At step number 6, I have a BTC message step, and this will set the profile for the Bluetooth headset to A2DP. I'll test the left and right ears. And then down here at step number 12, I have another BTC Connect audio message, and this will change the profile from A2DP to hands-free. Hands-free, I could still test the left and right ears, but what will follow, my HATS has a mouth simulator. I'm going to send a test signal through the mouth and capture the recorded response through the microphone of the headset, and we'll also measure the microphone, and that is also Bluetooth microphone. Okay, let me run the sequence and let's see what we got. So the first message is indicating to place the device in pairing mode. So as soon as I pull these out of its case, they will go into pairing mode. Okay, and I will hit enter. There's my device. And you can see the highlighted steps in the sequence edit window as this runs. Okay, I've switched profiles. Still testing the ears, then the microphone. Okay, and there you have it. My sequence has 3 display steps. So this first display step pretty much shows me the frequency response and distortion of the left and right ears using the A2DP profile. The center display will superimpose the A2DP response with the hands-free profile response. And of course, hands-free is a narrower frequency width, so you'll see the steep drop off at 8K. And this final display shows the left and right ears on the top display and the response of the microphone on the bottom display. So as you see, very simple to software communicate with the BTC, control changing profiles, very easy to build a sequence, and also very easy to run. Okay, so let's measure a Bluetooth speaker. I've got the Bluetooth sequence open in front of me, and this is a very, very simple sequence. You'll see on the left, I'll simply analyze the speaker's frequency response and THD distortion. And the sequence itself has some of the elements that we saw in the headset sequence. Here we have the BTC message steps. So that's software control that will query for Bluetooth devices, pair it, and then enable the Bluetooth audio. And down here, again, that's the frequency shift step. This will force alignment of the stimulus and response prior to doing analysis. So let's run this and let's see what we have. Okay, and again, I'm prompted to put the device in pairing mode. So let me turn this one on.
Mini Gem box is in pairing mode, waiting to pair with your device.
Okay, great. So I'm paired. I'm just going to place the speaker in front of this reference microphone. Okay, querying for Bluetooth devices. There is my jam box. And you'll see the sequence steps highlight on the right. You heard the 1K pilot tone. And there we have it. Top display is the frequency response. And again, this is a very small speaker, very little low frequency response, so there's a very steep drop off at 100 hertz. And then we have the THD curve on the bottom. So that is a very simple Bluetooth speaker test. I'd like to extend a special thanks to Christopher Hett of Portland Tool & Die for joining. This concludes our presentation today. Thank you again.